patience, my mind is not sane. I'm beyond insane. Don't turn bad, 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 Nakshi UKZN, gisihat fusanyas, shapata black ya imposa. You'd swear I'm closer. Bad, 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 Nakshi UKZN, gisihat fusanyas, shapata black ya imposa. You'd swear I'm closer. Carla, yo la feel like I will have no one sing it up, but just give me them my bandad. You're a spell of bad pants. Put your hands. Got it all. Got it all. I don't have no fast seats. Chakala, sick of it to hot seats. Saddle leg, saddle leg, saddle leg, saddle leg. Good car.
Good morning, everybody, and a very warm welcome to all our postgraduate students, academics, our industry partners, partners from government and the general public. It gives me great pleasure to begin this year's PRIS, our Postgraduate Research and Innovation Symposium, on behalf of the Vice Chancellor, Professor Nana Poku. The Postgraduate Research and Innovation Symposium is one of the premier events in our university's calendar. And it generally showcases the cutting-edge research carried out by our postgraduate students in all spheres of science from the 5 schools in our college. I look forward to a very interesting 2 days where we have oral presentations today and then the flash presentations tomorrow, where our students are going to be talking about the work that they've been carrying out for the last year or so, try to present them to you to get an idea of what they do day in and day out in our laboratories and fields. This is going to culminate tomorrow into our prize giving, where we are going to have some lucky draws as well, and to award prizes to our first, second, and third winners in each of the categories. We're also going to have a special prize this year about impact, and we want to see the audience trying to get involved here and voting for the students that have made the best impact in their talks on the environment and in society. So I look forward to those polls that we're going to carry out and see how you interact with us to let us know who has made the best impact in these 2 days. So that's going to be very exciting. So we look forward to an exciting 2 days, and these 2 days are generally for our postgraduate students. So I hope you make the most of it. It's your 2 days. It's very unlucky that we can't meet face to face like we did pre-COVID, but I see now it's the second time we're doing it online, and we're probably getting used to it. And I'm almost certain that in 2022, we're going to be back face to face, where I can meet each of you, have a cup of tea or coffee with you during the break and get to chat, which is really what a conference is about. But nevertheless, we're making the best of it during COVID times, and we're going to hold this year's Postgraduate Research and Innovation Symposium on the online platform. It gives me great pleasure to welcome our guest speaker today, Professor Neil Turok. Professor Neil Turok holds a PhD from Imperial College in London, and he obtained that in 1983. He was born to anti-apartheid activist parents who both later served as members of parliament in the new South Africa. Neil now holds the Higgs Chair of Theoretical Physics at the University of Edinburgh in the UK. He also holds the Niels Bohr Chair at the Premier Institute for Theoretical Physics in Canada, where he is the Director Emeritus. So we look forward to a very interesting talk, Neil. You know, on talking to some of my colleagues earlier on in the week, some of them commented that Neil Turok is one of the best speakers he has ever heard. So that you know you're going to enthrall us like you did him as well, and we look forward to your talk. So without further ado, Neil, I'm going to hand over to you to give the keynote presentation for the Postgraduate Research and Innovation Symposium of 2021. Over to you, Neil.
Thank you very much, Neil Koorbanally, to distinguish us too. First, a very warm welcome to everybody in the symposium. Thank you for joining us this morning. I'm very jealous of you, basically, because you're in Durban, I hope, or somewhere beautiful, whereas I'm in cold, rainy Scotland. And secondly, I had to get up 2 hours earlier than you. So please excuse me if I sound a bit sleepy. I want to, we are two Neils, and I'm going to bring that up a little bit later. And also, I'm also going to give all of you, I gather most of you are postgraduate students. I'm going to give you a little bit of important advice at the end of this talk. So please hang on for that. Okay, so let me start. And my topic is a small one. It's the universe. And I'm going to tell you a little bit about my own history, how I got involved in thinking about this small topic, and my perspective on it, which is unusual, but tremendously exciting, at least to me. So first of all, let me begin with the origin of all of this, thinking about the universe. Of course, our main tool in doing so is mathematics. Theoretical physics is essentially the application of mathematics to nature, the real world, and also to designing new things, like computers, like smartphones, and all of that. It all originates from the same source. And mathematics, of course, originated in Africa. On the top left, you see the Blombos stone, which is about 80,000 years old, and shows somebody in the Cape was carving pictures of equilateral triangles onto a stone.
Sorry, excuse me, Neil, are you sharing your screen? We can't see your screen.
Thank you very much. Yeah, like I said, it's too early. Can you see it now?
Yes, we can see it.
Yes.
Right.
Can you? Well,
yeah, you didn't miss much. You missed this slide where I just said that. Okay, thank you very much, Yin-Zhe, for prompting me. So top left, you see the Blombos stone with equilateral triangles found in a cave in the Cape, the world's oldest mathematical artifact. And so clearly our ancestors in Africa were beginning to do mathematics. Top right, you see Nabta Playa, the first astronomical observatory in the world. It's in southern Egypt, near to Sudan. And at the bottom, you see the Great Pyramids of Giza, which were the first great constructions that we know of course, using a pyramid of fundamental mathematical object. What about counting and numbers? Well, this is one of the oldest. This is the oldest artifact, which shows people were using numbers. 20,000 BC, discovered in the Eastern Congo, near to Rwanda. And what is going in, it's two sides of the same bone. This is a thigh bone of a baboon. And what's carved into the bone are all of the prime numbers below 20. It's a very remarkable object that indicates people were really counting quite seriously as long ago as that. So this mathematics, of course, developed into more famous things like Pythagoras' theorem and Euler, the famous Greek mathematician, and eventually in the Middle Ages was applied by Galileo and others to figure out how the planets and the moons and the solar system works. And as I'll come back to at the end of this talk, one of my goals is to see this mathematics and mathematical science brought back to Africa so that Africa becomes a world leader again in that field. A little bit about myself. When I was 17, I went to Lesotho. Many of you should recognize this terrain. This is a typical hut in Lesotho. I stayed in a hut like this. I taught in a mission school. I taught maths and science to kids there in a village. And I would say my main discovery was that there's there's every bit as much talent in Lesotho villages as there is in London, in England, where I happened to do my schooling. Just that the kids in the villages don't have access to the same opportunities, the same teaching, the same resources. And so this experience moved me very profoundly. The kids were extremely bright, and I won't start telling stories about them because that will take the whole talk. But they really impressed me with how clever they were, how motivated they were, and that moved me profoundly and made myself, later on in my career, start the Maths Institute in Cape Town, which I'll mention at the end. I was fortunate to know various remarkable people in my career. On the left, you might recognize Stephen Hawking. In the middle, Nelson Mandela. Of course, he knew my parents well through the anti-apartheid struggle. And I only met him once at this event, but he was extremely gracious. And he didn't know anything about Hawking and was very confused by Hawking's voice coming out of the computer, because you must realize Mandela was in prison while everyone else was learning about computers. And so it was a strange meeting. But as soon as I mentioned my name to Mandela, he said, "Ah, the son of Ben and Mary." And indeed, he remembered them. On the right, you may see Pick Botha, who played a key role in the compromise reached between the National Party and the ANC, which allowed the transition to democracy. A remarkable person who was actually profoundly interested in cosmology and had met Stephen Hawking earlier. And then David Block, who's a professor of astrophysics in South Africa. So this is my background. It's the struggle in South Africa. And actually, in my scientific career, this has given me something to draw on, which has helped me enormously. And encourage all of you, whatever your background, whatever your origins, whatever your struggles and difficulties, and we had many. My parents both went to prison, my father for 3.5 years. And those difficulties, when you have come through them, those are your main source of strength. And you should apply that in your scientific or your intellectual career. It's fundamental to you. So I'm going to tell you about this. This is a picture of the universe. And it's a very rather beautiful artistic representation. You can see the solar system in the middle with the planets going around the sun. And then as we look outwards in space, we are actually seeing backwards in time, because light travels to us from the early universe or from objects to us through space. So when we look outwards, the further we look, the earlier we see the universe or the object that was emitting the light. So if we look out as far as we can see, out to this red ring, this is of course a sphere which surrounds us. I'm just depicting a circle, but we're actually surrounded by a spherical surface. And whatever direction we look outwards in, we see this ultimate surface, if you like, the red ring, that we are seeing when it's approximately 14 billion years ago. The universe was very ancient when it emitted, and very near to the beginning when it emitted that light. So going backwards, we see the galaxies, the first galaxies, the first stars, and then going backwards even earlier, we see this rather strange web-like structure, which is the structure that first formed in the universe. That the very early universe was extremely smooth, had tiny ripples of density variations throughout space. And as the universe grew and expanded, those ripples collapsed into galaxies and the structures which we now see all around us today. So we're incredibly lucky to have this archaeological record of the universe going back to the red ring. The red ring is when the light was first released from the hot plasma of the early universe. Early universe was full of electrons, atomic nuclei, and photons. But at this point in time, at the time of the red ring, the electrons and the atomic nuclei combine to form atoms, which are neutral, and they don't scatter light very efficiently. And so then the light was more or less free to travel through space to us. And we detect this radiation from the Big Bang today. You'll see another ring outside the red ring, the blue ring. That's the initial singularity. That's the beginning of everything. And although in this picture it looks like a big blue circle, with our understanding of gravity, actually that was a point. It was a single point, because the whole universe was smaller at early times. And at this time, it was the size was 0. And so that's the Big Bang. And you won't be surprised to find that that is my obsession. What happened? What happened there? Where did it all come from? And every single thing we see around us today came out of that remarkable event. And what I'm going to tell you is that we've got a real chance of understanding that event right now. And I'm going to try to explain it in this talk. Now, there are several mysterious things we see in the universe, not many, but a few, and 2 of them are particularly mysterious. One is the dark matter. This dark matter is not atoms, not made of atoms. It's made of something else. It doesn't scatter light. That's why it's called dark matter. But it does have gravity. And we believe this was very important for attracting the matter into the galaxies that were forming here. So this process of galaxy formation was assisted by the presence of this dark matter, which clumps under gravity. And here we see a picture. I won't go through it in detail, but you can see an X-ray picture in red, a gravitational lensing picture in blue, and then the ordinary optical picture in yellow. They've all been superposed. And basically what this depicts is one clump, this right-hand clump, which actually passed through the left-hand clump, leaving a wake behind it, just like a boat leaves a wake on the surface of the water. And so we can reconstruct the history of this event and learn how much dark matter there is, because that bends the light in this gravitational lensing, and how much ordinary matter, because that's the matter that shocks and forms this structure you see. So we learned about that. We continue to learn about this dark matter, but we don't quite know what it is. Though I will tell you, I think I do know what it is very shortly. The dark energy is very mysterious. Here's a very expensive picture of the dark energy. I hope you can see my screen clearly. Yin-Zhe, can you see the dark energy?
It's completely black.
Good. Yes, that's the dark energy. So this dark energy makes up 70% of all of the energy in the universe. It dominates the energy in the universe. And it's the simplest kind of energy you can imagine. It's absolutely uniform in space, no structure. It doesn't clump under gravity. In fact, it repels itself and it causes the universe to expand exponentially. It's really amazing stuff. It's like cosmic dynamite. And this is 70% of what there is in the universe. So in the future, the universe is going to expand very rapidly and just become dominated by more and more by this stuff. Everything else will be diluted away, leaving empty, vacuous space. And so it's very mysterious stuff, only discovered 20 years ago, and actually anticipated by Einstein. And the reason he anticipated, yes, of course, he was clever, but he tried to write the very simplest cosmology. Okay, what would be the simplest universe with his equation? And the simplest one is with some kind of energy like this that has no structure, absolutely uniform in space. It doesn't even change in time. It doesn't dilute. And there it is. So it turned out that Einstein anticipated this 100 years ago, over 100 years ago. And indeed, it dominates the universe today. Now, here is everything we know of in physics, all the particles and forces. And at first sight, it's a strange pattern, but not really so complicated. We have quarks, which make atomic nuclei. We have leptons, like the electron, which orbits atoms. And then we have more sort of ghostly particles called neutrinos. And these are the particles which have been discovered in particle accelerator experiments. There are 3 generations. If you take a look at the columns here, there are 3 columns. They're broadly similar properties. They only differ in their mass. They get heavier as you go up the families. They all couple to the Higgs boson. And I'm very fortunate to be the first Higgs chair in theoretical physics in the world. Higgs is a professor at Edinburgh. He's now 92, and he won the Nobel Prize for postulating the existence of this Higgs boson, which plays a key role in determining the properties of all these particles. So it couples to all of them, and that's very important. And then we have the forces, the photon involved in electromagnetism, and then the nuclear forces, which have similar particles associated with them. Then we have the right-handed neutrinos, and those play a very important role in particle physics. Even though they are too heavy for us to produce them, you cannot produce them in a lab because they're too heavy, they mix with the left-handed ones to give the left-handed ones a very tiny mass. And so you can think of a left-handed neutrino as it travels through space. It's very light, almost massless. So it's traveling near the speed of light, but something slows it down. And what slows it down is that it mixes ever so gently with these right-handed neutrinos, which are extremely heavy. So if you like, it travels along, and then from time to time, it oscillates into a little bit into a right-handed neutrino, which is very heavy, and then it goes back into being left-handed. And that mixing is responsible for the left-handed neutrino masses, which we actually measure in experiments. So if you like, the left-handed neutrinos are really probing some very heavy objects, which are too heavy for us to make in a laboratory. So this was all known. And then, of course, the blue ring around it is gravity. Gravity couples to everything. It holds everything together. And it's the most important force in the universe. Now, I have to tell you a little bit about my own perspective. So I joined this field in the early 1980s. And the paradigm there was to add more things. You see, this is how the model was built. we built a new accelerator, we discovered a new particle, and we added it to the table. That was the traditional way to do particle physics. And when I joined, theorists like me were still doing that. In fact, even though there wasn't any evidence because we weren't able to make accelerators powerful enough to see more particles, we kept building more and more complicated models. There were grand unified theories, supersymmetric theories, supergravity, superstring theory, extra dimensions, M theory. Okay, so this was, the models were elaborated and elaborated in the hope that magically everything would unify, that by adding more to the model, suddenly everything would simplify and become more compelling. So after several decades working in this area, I reached the opposite conclusion. Okay, I reached this adding, by the way, didn't work. After 1980, there's been no evidence for new particles. And the largest experiment ever built, the Hadron Collider at CERN, switched on, discovered the Higgs boson, fantastic success, and nothing else, nothing, right? So 99% of particle theorists had postulated extra particles, which it would see, and they were not there. The conclusion I have drawn is that nature is simpler than we thought. It's still puzzling. They're big puzzles, but the way to solve those puzzles is to think more deeply. Don't just continue adding things to your model. You know, you have to understand things more deeply. So my recent work has all been in that vein. It's foundational physics, re-examining the basic laws of nature in the hope of solving puzzles that way. And I've come to a very surprising conclusion, which is that what we have here is sufficient to explain everything. We don't need to add anything. It's all there. You just need to think more carefully. Now, the first thing I'll tell you about is these right-handed neutrinos. I mentioned the problem of the dark matter. The dark matter doesn't couple to light. Well, neither do these guys. Traditionally, people suppose these were unstable. So if they were created in the Big Bang, they would decay. Amazingly enough, 2 years ago, we proposed that one of them is the dark matter. And the reasons we were able to make this work theoretically are very fundamental. And I'll come to them in a little bit later, the fundamental reasons. But the message I want to convey is, if you want to do something profound, think deeply. Don't just follow fashion and do what everyone else is doing. And if you think more deeply, the solution may be right in front of you. Okay, so now we have these pictures of the universe. This is a picture of that red ring. So we're inside a sphere. As we look outwards, we're surrounded by this sphere, which is the time when light was released from the Big Bang and traveled to us. So we can look at that red ring or the interior of that sphere. And this is what we see. We see these little ripples emerging from the Big Bang. So an extraordinary detail. And I love this quote from Shakespeare, which I think represents it very nicely. It's a vast shore washed with the furthest sea. And the early universe is indeed like a sea, and these are like ripples on the sea. This glorious picture was made by the Planck satellite. Now, Jim Peebles, professor at Princeton, did some of the first calculations which predicted what we would see. You see, you look at this picture, it looks quite random, right? You might say, oh, well, it's like tea leaves in a teacup. Why should I care? Obviously, there was something, but there's no structure here. That's where you're wrong, because if you Fourier transform this picture, so a mathematical operation to detect the normal modes of vibration of the universe, when you Fourier transform, you get this beautiful curve. And what's really happening is like the ringing of a bell. The Big Bang is like the striking of the bell, And the bell is the whole universe, and it's full of this plasma, which has sound waves, just like a bell does. And they oscillate, and those oscillations are what you see here in this Fourier spectrum. So Jim Peebles predicted the red curve, and I was really thrilled when he was awarded the Nobel Prize very recently for making this prediction. And as you see, it fits beautifully with the data. And so amazingly enough, cosmology is now rather a precise science where we can predict the basic properties of the universe much more accurately than anyone can predict anything in, let's say, biology or chemistry even. And so cosmology really has become a mathematically precise science. Now, I was fortunate to get into the game in the 90s when no one had calculated the polarization. So as well as the intensity of light, which you see in this picture, light can be polarized. And you know that when you wear Polaroid spectacles, they cancel out some of the reflected light because reflected light tends to be polarized. So polarized light has a different pattern, and we were the first to calculate it. And here it is, the correlation of the polarization with the temperature. There is our theoretical curve. There is the data on top. The amazing thing about this is there are no free parameters in this fit. Once you fit all the parameters to this curve, the intensity curve, you predict this mathematically. Now, we didn't do anything original to do this. We took some mathematics developed by the Indian astrophysicist Chandrasekhar in the 1920s. This is ancient stuff, propagation of light in plasmas. And we just applied it and calculated it, generalized people's calculations. And here's the fit. It's extraordinary. So I learned something very profound from this calculation, that something extremely simple and understandable is going on in the universe. And again, this has informed my current perspective. Here are the latest measurements. And here you can see again these oscillations with maybe 15 peaks and troughs, everything lining up beautifully with theory. The universe is absolutely comprehensible and describable with mathematics. Now, let me tell you what most people are doing who do fundamental physics, fundamental theoretical physics. You may have heard of string theory, and you may have heard of inflation, cosmic inflation. It's a theory of how the universe became so big and smooth and where these fluctuations came from. And people put these ideas together to get the multiverse. Okay, here's a picture of a multiverse. So just imagine that the universe is very, very different from place to place. There are regions where one set of laws holds, there are regions where another set of laws holds. In between, there are these inflating regions which are going crazy. And the universe is completely chaotic, random, unpredictable on large scales. So I'm not going to tell you the details of this, just to say that some very, very smart people, in fact, the majority of very smart people in theoretical physics, believe in this kind of picture. I don't. Okay. I have come to the view that the majority of theorists in my field went wrong. In fact, about the time when I started, about 1980, people started to add more and more ingredients to their models. And what did they end up with? Well, chaos. It's no surprise, and it can happen in any field, that your models get too complicated and you end up with absurd conclusion. And this is the ultimate absurdity. It doesn't predict anything about the universe. And it's in extreme contrast to the observations, which are amazingly simple. And so something went wrong. Now, that is a wonderful opportunity, because if most people have turned left and the true path is on the right, then take the true path, and you have an opportunity to really do something important. So I believe the multiverse is a dead end. And now I'll explain why. That's my humble opinion. I'll explain why. So a couple of years ago, we proposed this. This is the mirror universe, and this is the way we explain the dark matter. So here you see the Big Bang, where the whole universe was at zero size, and the universe emerges on the right. You see the nuclear particles, atoms form, galaxies, and finally, the dark energy takes over and causes space to expand exponentially. What we realized is that the fundamental laws of physics have a symmetry. It's called CPT symmetry, charge conjugation, parity, and time reversal. Don't worry about that. It's a symmetry which relates matter to antimatter. It reverses time, and it turns space inside out, which roughly speaking is exactly what happened at the Bang. And so with this symmetry, we realized there really should be an image universe on the other side of the Big Bang. It should be full of antimatter, not matter, and it should be collapsing, not expanding. One way of saying this is that the Big Bang is a mirror. It's not really a source of everything. Somebody didn't put everything in the bang and let it go. The Big Bang is really a mirror in which ourselves are reflected in a previous existence. But this previous existence is literally a mirror image of us. You see, if I look at a mirror and I'm right-handed, I will see a left-handed person in the mirror. It's not the same as me. And this is exactly the same here. As we look back to the Bang, we see an anti-universe, which is literally the mirror image of ourselves. So that was our theory, and we were able to use this theory to predict how many right-handed neutrinos were formed in the Big Bang, and therefore how many would be there to make up the dark matter. And right now, that's the simplest and most economical and most predictive theory of dark matter, which there is. And it makes some very precise predictions, which will be checked in the next 10 years. So here's the mirror. We look back to the Big Bang, and this is the mirror image universe. But it's really identical to ourselves, and it's more like a device. You know, when you do the theory of light and electromagnetism, and you want to solve the problem of light reflecting off a mirror, we use the method of images. The method of images, you say, forget the mirror, let's put the person who's my image on the other side and make them left-handed. And then we solve the equations without the mirror, but with the mirror image behind, and you get the right solution. So this method of images really underlies our theory of the Big Bang. Without adding any new particles or assumptions, we can explain the dark matter as one of the right-handed neutrinos, the matter-antimatter asymmetry, why there is more antimatter, why there is more matter than antimatter in our universe, and the converse in the anti-universe. We can explain the arrow of time. We can explain why the vacuum energy is nearly but not quite zero. We can explain the origin of these density variations. And then the most exciting thing, and this is really just in the last few weeks, we've realized we can explain why the universe is flat. This was, in fact, the great idea which drove the dominant theory of inflation starting in 1980. So the puzzle is the following. Why is space so flat? You see, Einstein's theory of gravity allows space to be curved. The universe could be, according to Einstein, a little sphere, curved, very curved up. But it's not. It's very flat. And a simpler parallel is to think of the surface of the Earth, right? The surface of the Earth where you live, you're not really aware of the curvature of the Earth, right? The Earth is a sphere, but we're not aware of that as we wander around in a small area. It looks pretty flat. Well, the universe is the same. And so inflation was the idea that you have exponential growth of space driven by a new ingredient people added to make this expansion happen. So you literally add the dynamite, which will blow up the universe. As it expands, it stretches and flattens out. Okay, so it was a mechanism to make the universe flat. What I've realized recently is that within this picture, one can calculate what is called the gravitational entropy. This is an idea going back to Stephen Hawking that I showed. In other words, you can calculate how likely it is for space to have different properties. And it turns out the most probable universe is flat. The reason it's flat, I'll show you the picture. So why is the world flat? Here's a picture of the Earth, right? Why is it flat? Here I am in Edinburgh, okay? And space looks fairly flat in a small region of the surface of the Earth. But notice how round the Earth is. Why is the Earth round? Okay. Did somebody come and polish it? Was it, or did somebody make a round universe? Was there some mechanism? No, the reason why it's flat is A, because of gravity. Gravity pulls things in. But B, more fundamentally, because of entropy, because of thermodynamics. You see, if the Earth was lumpy, gravity would pull the lumps down, and then their energy would be dissipated in friction. Because when you force these rocks to move past each other, you release heat. And why does that go one way? It is because, why do the rocks go down and they don't go up? The reason is because the heat, the production of heat is irreversible, and that's driven by entropy. So the reason the Earth is round is because of gravity pulling things in, and then friction dissipating the energy into heat. Why does energy dissipate into heat? Because that's how you produce more entropy, okay? And that's why the Earth is flat locally. It's flat because it's big, okay? It's as simple as that. If we had a tiny Earth, like a water drop, of course it would be curved. It would have to be curved. It would still be round, but it would be very curved on a small scale. So the Earth is flat because it's big. I have found the same answer for the universe. The universe is flat because it's big, and it's as simple as that. Now, I want to end by telling you a bit about AIMS, the African Institute for Mathematical Sciences. We've been running now, I was privileged to start this institute in Cape Town in South Africa in 2003. And we've been admitting students since then. We have about 100 students at a time in South Africa. And then we have 4 other centers, one in Senegal, Ghana, Cameroon, and Rwanda. Each center has between 50 and 100 students taking master's programs in mathematical science. And so far we have 2,500 alumni, of whom about 800 or 900 have now gone to PhDs, either in progress or completed, in all fields of mathematical science. So it's really a very exciting institution, probably somewhat like UKZN, very multicultural, full of creative and excited young people getting into serious science. Why is there an opportunity? Well, it's precisely because of the lack of opportunity in the past. Okay, so Africa, as you know, has been largely marginalized in science. It's very underproductive as a continent in science, not because of its own fault, but because of colonialism and the history of being invaded, being occupied, and being held back. But right now, Africa's population is very, very young and is growing fast. And so when we project the youth population into the future, you can see that Africa is going to overtake China, for example. And whereas all the other continents, the population is declining, Africa is growing extremely fast. And that's what you need for science. You need bright young people. And there is an abundance in Africa, and there will be even more of an abundance. It's absolutely essential to allow these young people opportunities to enter science. It will be good for Africa, but also very good for science. So here are some of them. This is AIMS in Rwanda, beautiful institute. Here are the students. I hope you get a little flavor of the place from this picture. These students are going into very high-level science and already beginning to change things in the world of science. So thank you very much for listening, and I'm very happy to answer questions.
Thank you, Neil. Thank you for that excellent talk. It's also given me a new perspective on the universe. I've never known that there might be another Neil Koorbanally out there in another dimension, somewhere in an anti-universe. so thank you very much for that. I'm going to hand over to Yin-Zhe in a few minutes, but before I hand over to Yin-Zhe, I wonder if you could answer this or get your perspective on black holes. You know, black holes are one of the things that intrigues many people and many students. So I wonder if you could give us your perspective on black holes, what they are, and you know how they work.
Absolutely. So thank you for the question. In fact, it's one of the things I omitted from my slides because I didn't have time. Let me see if I have, I don't have it in this slide set. Yes, so let me just talk about black holes. So let's see, am I sharing? I'm not sharing my screen, right? So,
no, you're not.
Okay, good. So yes, so black holes. Black holes are a consequence of Einstein's theory. They're not avoidable. Okay, so even though Einstein himself didn't realize it, very quickly people, when they studied these equations, they realized that if matter, if you have a star that is beyond a certain size and it's pulled together by gravity, when that star collapses, it will collapse into a black hole, and that is unavoidable. So they are a direct consequence of Einstein's theory. You can describe them using Einstein's equations. The amazing thing today is that we can see them. And so we are 100% sure about black holes. Almost every galaxy has a giant black hole in its center. We have one in its center. In fact, the Nobel Prize was recently awarded to astronomers who had seen the black hole. The way they see it is by stars falling into the center of the galaxy, and then they get a kick. They fall in, and then if they're close to the black hole, suddenly you see this big gravitational kick. And so it's very dramatic. There are movies of this online. These are real movies, not fictional. And this shows the stars being kicked by the black hole. So we know its mass, we know its size. There's a wonderful experiment called the Event Horizon Telescope, which actually uses radio telescopes all across the Earth together as a giant telescope. So in fact, the whole Earth becomes the lens of a big telescope, which is looking at the galaxy center, and using that, they've been actually able to make an image of the black hole itself. It's a dark disk surrounded by the glow of the plasma that's falling into it. And I think very shortly, this collaboration, the Event Horizon Telescope, will release a movie showing you the gas as it is falling into the black hole. So we can now watch these things. The change in our field has been amazing. Okay, so we can, the universe is now our best laboratory for fundamental physics. We can see black holes, we can see neutron stars. I won't say it, otherwise I'll go on too long, but it's just unbelievably exciting. Instead of building particle accelerators, we just look at the sky And nature is providing us with the collisions between neutron stars. A neutron star is just a big atomic nucleus. That's all it is. It's just 3 kilometers across, but it's an atomic nucleus. And 2 of them smash, and you see the creation of heavy elements and all the experiments, you know, you could imagine. So nature is providing a physics lab for us in the sky. We see gravitational waves when black holes are merging with each other. They orbit each other and get faster and faster and faster. As they fall in, then they merge, and a puff of gravitational waves comes out. We can detect these now. Again, a Nobel Prize was awarded for that recently. And so we have access to black holes. Theoretically, they are the most profound, one of the most profound challenges at the moment. What goes on inside a black hole? You see, it's like the Big Bang in reverse, because if you go inside the black hole, you collapse to singularity. And so inside a black hole is literally like a cosmos running backwards in time towards a big, what we call a big crunch. Now, I've explained very, very sketchily our mirror theory. I was very delighted a month ago when I gave a seminar in Holland. I wasn't there, but the seminar was there. And in the audience was Gerard 't Hooft, who is one of the world's top theorists in particle theory, won the Nobel Prize for quantum field theory. And I explained this mirror theory, and he said, he said, that's exactly what the black hole is. So he has a description of a black hole, which he arrived at independently. And according to him, the black hole itself is just a mirror. When we look into the black hole, we actually see it's like a mirror of what's going on outside the black hole. And so, yeah, I was delighted that these descriptions seem to be merging, and we're reaching the same conclusions, which are both extremely simple and very predictive, and in sharp contrast to what most people have been doing. Okay, great. Most people are just building more and more complicated and arbitrary models. That's not how nature works.
Yes, great. Thanks, Neil. Yin-Zhe, I'm going to hand over to you now for the Q&A session.
Okay, great. Yeah, thank you, Neil, for your exciting talk. I just want to use this as an opportunity to advertise our UKZN Astrophysics Research Center, which are leading by Professor Koorbanally and myself. That we have been doing very, different exciting science, especially revolving around South Africa SKA. And if you are interested, you can search my name, Yin-Zhe on Google, or Astrophysics Research Center of UKZN on Google, and you will find our email and send us an email to express your interest. Okay, yeah, and today I'm delighted.
Yin-Zhe, before you go on, I omitted to mention that from my talk, but I've been very lucky to collaborate with 3 different groups at UKZN. One is in mathematical physics, quantum physics, and so Francesco Petruccioni, and then one is in genetics, where Tullio, I've forgotten his surname, but Tullio works, of course, very important in this Omicron variant for COVID detection. But the most important is with Koorbanally, who actually was my PhD student in Cambridge. And so I've worked with him in cosmology for a number of years. And Kavi is now leading the HIRAX project, which is a radio telescope to map this radiation from the Big Bang, and also to see objects like neutron stars and so on. So yeah, I should have advertised UKZN myself more, but I'm glad you did.
Yeah, okay, great. Yeah, today we do have a list of questions. Actually, some of them are really insightful questions. So, okay, let me, because of time constraint, let me just quickly go through. So two of questions, I would like to combine them about the circle, about the big circle, which you have shown at your earlier slides. And they ask, is there a boundary to the universe, and do we need to speak of universes? And does the blue and red ring means space has an end? Yeah, please.
Lovely. Okay, wonderful questions. And, you know, these questions have puzzled the best thinkers in cosmology for a long time. So does this represent the edge of space? Okay, is the question. You can see my screen, can you?
Yes, we can.
Okay, good. So does the blue ring represent the edge of space? So no, it doesn't. The way you should think about this picture, and it's a little bit difficult to conceptualize, but if I go to this picture, it's more like this. You see, so we're up here, the time is going vertically, and we live here today. And then as we look outwards in space, we're seeing backwards in time. Now, it's a little confusing, but you have to literally follow the light. You see, the way you have to do physics is by actually picturing what is happening. So a photon is a particle of light. It's being received by us up here. Let's say we live in that galaxy, okay? Where did the light come from? So it traveled backwards, outwards in space, right? As we're going back in time. So it goes back like this. However, the universe was expanding, right? So as we go back in time, the universe contracts. So this light ray, it's going outwards, but all of space is shrinking. And so the blue circle, where is the blue circle? Well, actually, the blue circle is about here, okay, where the light was released from this plasma. Sorry, the red circle is here, where light was released from the plasma. Now, the light would actually scatter very much in this plasma. But if we just imagine that it's not light, but it's, say, a gravitational wave, which scatters very little from plasma, this gravitational wave photon would have traveled this way and then back through the universe, right to the Big Bang. And that's the blue circle, okay? So the blue circle is this point, okay? How can a circle be a point? Well, it can, because space itself changes its size, okay? So you have to have this picture that actually the blue circle was a single point. Now, still a good question, is the point the boundary of space? And what I'm telling you is that no, the point is like a mirror, okay? But there was nothing, you might say, what is the mirror? You know, why does the universe have an edge at the mirror? Okay, it doesn't. It's just a boundary condition, what we call a boundary condition. And one way to say it is that, you see, the length of this structure, the universe, is variable. When you do quantum physics, nothing is rigid, everything varies. This length is also variable. When you calculate something, you must allow for universes of arbitrary length. Space and time are flexible substances. You must allow all of them. And so this is really a boundary condition, not a fixed boundary. Okay, and that's a subtle difference. But there is no edge to the universe. This is not an edge. The universe would continue in the same way. The line here is simply indicating the size of a given region of the universe, right? The universe itself continues in exactly the same form beyond this edge in the picture. It's just we introduce an edge in order to draw it, but there is no edge. So yeah, the answer to your question is that I don't believe there's any edge to the universe.
Okay, great. And among this list, I find there is a very insightful one. He asked, can the anti-universe theory provide a solution to the Hubble tension? And what other probes we can use to test this anti-universe theory? Yeah. This is from Raul. Yeah.
Lovely. Thank you for the questions. You allowed me to show this slide. Okay, so first question on the Hubble tension. Now, the Hubble tension, in my opinion, so you've got to be very careful as a theorist, not to be distracted by the latest results, okay? Because much of the time, the latest results are not correct for one reason or another. It's not the observer's fault, it's not the experimenter's fault, but these experiments are very, very difficult and very complicated. And there are many sources of confusion, okay? So some theorists will always be chasing the latest observations, and they will jump from one thing to another. And that is seldom the way to see something deep, okay? Because the observations, 9 times out of 10, they will just distract you. And that is the whole history of the subject. People have been arguing about the Hubble constant for 50 years, right? And anybody who tried to learn about the universe by following that argument, you know, would get nowhere. Okay, so I must admit, I don't follow it very closely. Probably it'll get resolved by one or the other observation being, you know, slightly wrong in some of its assumptions. Actually, it doesn't matter to me what the Hubble constant is. That doesn't really affect any of the issues I'm interested in. I assume there is a value, but and maybe one of the observations is correct, but I don't really mind what the value is. So you know, I leave that work to people who are more focused on observational issues. On the other question, what are the predictions of this model? So there are some really very strong predictions. If one of the right-handed neutrinos is the dark matter, then it must be stable. It cannot decay, okay? It turns out that the stability of one of the right-handed neutrinos implies that one of the left-handed neutrinos must be very nearly massless. Its mass must be 0. The reason is to do with how they couple to the Higgs field. But so essentially, to make the right-handed one stable, you must switch off that coupling. And it's the same coupling that creates the mass for the left-handed neutrino. And so the left-handed neutrino would be massless. So that's our prediction. That's a very, very strong prediction. So what is measured in laboratories are mass differences. There are 3 left-handed neutrinos, and you measure the differences between their mass. So we only know 2 numbers, the 2 mass differences, but there are 3 masses, and we don't know what the masses are yet. If we set the lightest one to 0, which is what our theory does, then we can actually predict all the masses. Okay, so that's what we've done. And we predict in this slide, the sum of the neutrino masses is either 60 or 100. You say, why do I have 2 predictions? The reason is because if you know the mass differences, one of the differences is small and one is large. Now, it could be that it's like this, with the 3 masses and the 2 biggest ones having a small difference, or it could be like that, 2 light ones, okay, and 1 heavy. This one is called the normal hierarchy, where you have 2 light and 1 heavy. And this one is called the inverted hierarchy. And so we predict a different number for the total neutrino masses in those 2 cases. So either 60 or 100 milli-electron volts, very tiny. Remember, the mass of the electron is a mega electron volt, right, or 0.5. So it's like a million electron volts. This is 1/100th of an electron volt, so tiny, tiny masses. You can measure these using cosmology, using the distribution of galaxies. It's really amazing. Again, the universe is this ultimate physics experiment. And this is from a recent paper using this legacy survey of space and time in Chile. It's a beautiful telescope, just been commissioned, will have data in the next couple of years. And using that telescope, an S4, which is basically like the Large Hadron Collider, but for mapping the microwave background radiation. It's a huge experiment, which is the biggest in the world. And again, to be done in the next 10 years. Put all those things together, you can measure the sum of neutrino masses to 12 MeV, and we're predicting 60, right? So we're predicting these masses. The sum of them is 60. The error in the experiment will be 12. So we're going to have a 5 sigma measurement of this prediction, which is pretty good. And that should be certainly within the next decade. So if this prediction is correct, I think probably what will happen, my guess is we'll prove the inverse hierarchy wrong first, unlikely to be inverse hierarchy, prove that wrong, prove this correct. Then I'm afraid, as far as the dark matter, no other theory will be anywhere near this one, okay? No other theory of the dark matter makes predictions as precise and is so economical. That's my forecast.
Thank you, Neil. And thank you, Yin-Zhe, for directing the Q&A session. Neil, once again, thank you very much. We really appreciate you taking the time out this morning. I know it's 2 hours, ahead there in Edinburgh. So it's early in the morning for you. So thank you for taking the time out. I think one of the nice things about having these postgraduate research and innovation symposiums online is that we can have guest speakers from all over the world. And we really appreciate, you actually coming out to take the time to talk to our postgraduate students today. So thank you for that.
Thank you. Thank you.
Ladies and gentlemen, I think we're now going to conclude this session here and to go away to our breakaway sessions. I now invite you to go to our website, pris.ukzn.ac.za, pris.ukzn.ac.za, where you will find links to the breakaway sessions. So if you're interested in attending the talks in each of the schools, engineering, agriculture, earth and environmental sciences, chemistry and physics, so forth, you may just click on the links on our website and it'll take you straight to that particular talk. So I'm now going to conclude the session. Thank you very much for your participation, and I hope to catch you at one of the breakaway sessions in future. Bye-bye, everybody.